split in half. The first part of this packet is what we're going to do in class. The second part is actually the video that you'll watch once we're done, or for tonight, for tomorrow, that kind of just goes through and continues to talk about chirality and chiral centers. So we're going to focus right now on what are chiral centers, how can we identify chiral centers, and then looking at enantiomers. So you've seen this a couple times before. We've been talking about isomers. Isomers are compounds that have the same formula but different structures. And we've seen that in a few different ways now. So constitutional isomers are compounds that have the same formula but different connectivity. So an example is actually something like, what did I have? Methoxymethane actually looks like this. I'm going to show you the full structure here. CH3. So we have an ether here. 2 carbons, 6 hydrogens, and an oxygen. If we look at ethanol, okay, so here's ethanol. Also, 2 carbons, 6 hydrogens, and an oxygen. These have the same formula, but they are connected differently. Those are constitutional isomers, right? When atoms are connected differently. We aren't going to look at constitutional isomers as much. We're focusing over here on stereoisomers. So we've looked at cis-trans isomers already. We looked at double bonds. We looked at the E and the Z designation. Right? Is it on the same side, on different side? We looked at it with chairs, wedge and dashes. And now we're going to focus on this part over here that's looking at isomers that contain asymmetric centers. So stereoisomers over here, all of this is dealing with what happens when the atoms are actually connected the same, but they're arranged differently in space. So one is a wedge, one is a dash, right? That's looking at stereoisomers. We're going to focus on these asymmetric centers. We're going to look at enantiomers, which are mirror images, and we're going to look at diastereomers as well. Diastereomers are what happens when they're not mirror images of each other. And so we're going to look at that more tomorrow. So that's looking at these asymmetric centers with isomers. So when it comes to chiral and achiral, so again, the way that we say it is chiral. And with these, we looked at capital letters in the intro activity. And I was going through looking at capital letters with different groups. Chiral objects. So in general, chiral objects have non-superimposable mirror images. That means you cannot lay the mirror image on top of the original. Your right hand and your left hand are mirror images of each other. I cannot rotate, right, one of my hands to lay it directly on top of the other and make it look identical. And so our right hand is chiral. Our left hand is chiral. Same with your ears, right? A car. If you look at the inside of a car, that's chiral because you have the steering wheel on one side. Achiral, those have superimposable mirror images. That means that you can lay the mirror image on top of the original and it's the same. They're identical. So a chair. A chair that looks like this, I can lay the mirror image on top and it's the same. A fork, right? A glass. You could probably come up with like different objects that you lay the mirror image on top. It's identical. So chiral has a mirror image that you cannot lay, so it's unique. Right? You cannot lay the mirror image on top. Achiral, you can lay the mirror image on top. And so looking at these capital letters, right? So just to show you these capital letters. Chiral letters, meaning that you cannot lay the mirror image on top. And I showed some groups this yesterday, like the letter F. Here's the mirror image of the letter F. I can't rotate this in any way to make it the exact same so that I can lay it on top of the original. Right? We can't rotate it. Achiral, so like the letter M. We looked at the letter C. Right? There are a lot of different capital letters. People use the letter B. But with the mirror image, you can either lay it right on top or you can rotate the mirror image in a way that it will lay right on top of the original. That's looking at chiral versus achiral. So the achiral letters, you can lay the mirror image on top of the original, and it's the same thing. And so now we're going to look at it in terms of molecules. So chiral molecules have what we call an asymmetric center. It's a chiral center. Right, you're going to see it as asymmetric center, but we're also going to use the term chiral center when it's attached to 4 different things, right? 4 different groups. And so when we look at this carbon, it's attached to 4 different groups. That's a chiral center. When we look at 2-bromobutane, we have this carbon is connected to a methyl, it's connected to a hydrogen, an ethyl, and a bromo. Those are 4 different groups. That makes this a chiral center, and you see it designated with that asterisk. Tells us that it's a chiral center. And so just to show some other asymmetric centers or chiral centers, you're just looking at what is it attached to. So this carbon, you have it attached to a 3-carbon chain over here, a 4-carbon chain, an OH, and an H. Right? 4 different groups gives us a chiral center. And if you say, what's the importance of a chiral center? Well, in order for us to be looking at these enantiomers, diastereomers that we're going to look at tomorrow, we have to have a chiral center. If it doesn't have a chiral center, it's not going to be one of these stereoisomers. Right? It might just be identical, or we'll talk about different names for what happens if it's not a stereo center, but it's arranged differently. So we'll look at some of these different terms. When we look at this one, so here's a carbon. I noticed this, it's attached to an OH. 1, 2, 3 carbons. 1, 2, 3, 4 carbons. And then there's also a hydrogen. So this carbon right here, if it asks us to designate, this would be the carbon that we would designate as the chiral center. 4 different things. If this was 4 carbons on this side and this was a 4-carbon chain on this side, it wouldn't be a chiral center because it wouldn't have 4 different groups attached. So looking at additional, this is just showing different compounds that have a chiral center. So when you look at 2,4-dimethylhexane, it shows us the chiral center here. Now I want to look at this second bond line structure. All right, you're looking at where are there carbons connected to 4 different groups. And sometimes people will look and they say, well, this one, right, maybe this one, because we know this is 2 hydrogens, we know this is 2 hydrogens. But when you look at this carbon, if I look at this carbon first and I determine if this is a chiral center or not, what is one of the things that this carbon is connected to? Methyl. Right, a methyl. So here's a methyl. What else is it connected to? Methyl. Right, another methyl over here. And then you have the hydrogen, and you have the rest. Right, this is all considered one group. Methyl and methyl, those are not different groups. This is not a chiral center. This one is. Right, this is a chiral center. But this one is not a chiral center because it's connected to 2 methyls. It's not 4 distinct groups. Now, can some molecules have multiple chiral centers? Yes. And don't worry, we will be looking at those eventually. Right? But just remember that for it to be a chiral center, we need to make sure that there are 4 different groups. So, chiral and achiral molecules. This is similar to the models that you built yesterday with the model kits. And what I like about the model kits is that it lets you actually hold the molecule and rotate it. So when you look at, this original molecule connected to 4 different groups, this is a chiral center, which makes it a chiral molecule. It has a chiral center. When you look at the mirror image, so imagine a mirror here. Here's your mirror image. What you want to ask yourself, if you're like, okay, can I lay this on top of this and it's the same thing? Think about rotating. you can rotate the molecule. If you rotate the molecule, you're like, okay, well, if I rotate it, right, rotate it this way maybe, can I make it the same? And when you rotate this, keep bromine up. Your goal is to get the ethyl on this side. And when you do that, when you rotate it, your hydrogen ends up being on a wedge, your methyl ends up being on a dash. Those are not identical molecules. And so these are enantiomers. Right? When you look at this, and you're looking to see, okay, is this the same or not? Well, now I have two hydrogens here. When you rotate it, it doesn't matter. One hydrogen is a wedge, one hydrogen is a dash. Now when you're trying to figure out, okay, is this identical? Is this an enantiomer? Well, it can't be an enantiomer if it doesn't have a chiral center. So one thing to kind of make note of is this says it's an achiral molecule. Its mirror image will be superimposable. You can lay it on top. Because in order for it to be an enantiomer, it needs to be a chiral molecule. That's the first thing that we can look at. So chiral compounds have non-superimposable mirror images. Achiral compounds have superimposable mirror images, right? Achiral compounds are identical molecules. If you have two things, two molecules, and you're like, okay, this is achiral, well, that means if they give you another one that looks like it, it must be identical, because it doesn't have a chiral center. So then, looking a little bit more at enantiomers. Right, they are mirror images of a chiral compound. So I'm trying to give these mirrors. This is, again, if using model kits help you, by all means use a model kit. But you have this mirror image. So you are literally just drawing, right, the mirror image of it. This is a dash, wedge, right, in the plane. If you are trying to ask yourself, okay, is this an enantiomer or not? You want to see, can I rotate it to make it the exact same? And for this, the answer is no. Because your wedge and your dash, that's three-dimensional, that plays a role. If you try to rotate it, you can't actually make them the exact same. So these two are enantiomers. They are different compounds, and we're going to look at how to designate between the two Friday, if not next week. R and S designation, we're going to talk a little bit about it today. Those that are in AP Bio have heard a little bit about these because of the difference in a wedge and a dash, what that could potentially do. But enantiomers are different. They're isomers. So they're just connected differently in space. So when we look at enantiomers, right, so these two are enantiomers. Here's a trick. I don't know if it's a trick or it's just the definition of an enantiomer. Enantiomers can be drawn by switching the position of any two groups on a chiral center. Switching position means switch the wedge and the dash on a single chiral center. That means this is my chiral center. I have H as a wedge, F as a dash. If I switch those two positionings, we've created an enantiomer. Right? It's a non-superimposable mirror image. And it might take a little bit because you have to think about what does it look like in a mirror, how can you rotate it. But if you switch the wedge and the dash on a single chiral center, you have created an enantiomer. So just think about changing the wedge and the dash. Now, here's where we kind of tie in a little bit of AP Bio, or I guess just Bio in general. We're going to talk about R and S, like I said, later when we're designating the difference between the two. But this gives a really nice visual on the difference between these two. Here's the original chiral molecule. This is the mirror image. Right, so hopefully you can see how it's a mirror image. They're on opposite sides, right? So here's one molecule. Here's its mirror image. This plays a role in bio because notice if you have these receptors at different binding sites, they have to fit in perfectly. Well, once you have an enantiomer, It's the mirror image. When you're looking at this, you're trying to figure out, okay, is there a way that I can rotate this to make it fit into that receptor? Well, I say, okay, well, if I rotate it around this way so that the circle is here, I rotate it one position. Now the circle's over here, but now the triangle is here and the square is here. It's a completely different molecule. Right? Just it's arranged different three-dimensionally.
What if you put the green circle up and have the purple circle on that side?
Well, then you'd be looking at, I mean, yeah, technically. Right, if you put that, but these are two different things. So if you're looking at like a different enantiomer, right, looking at the binding site. Now, just to give you some kind of real-world examples of these enantiomers, we didn't do the reading or the video on thalidomide, but there's actually a distinct difference between the two. Our thalidomide, so again, this R and S designation, our thalidomide is a sedative. It's given to help calm. S-thalidomide is what they call a teratogen that was actually given to women in the 50s that caused birth defects. So there's this big thing called the thalidomide tragedy, where the S-thalidomide, they thought because the R isomer, the R enantiomer, was a sedative, that they were using the S enantiomer in pregnant women. And then they found, right after all these pregnant women had their kids, there were lots of birth defects. And they found that it was because of S-thalidomide being given to them. And it's all just because this is a wedge, this is a dash. It's the difference between, right? These are two different molecules. They're isomers of each other, but it can cause something as drastic as like causing disturbances in like embryos. Another example, I think this is the one with the AP Bio tie-in that you talk about. And it's looking, again, the one difference between a dash and a wedge. You have the active ingredient in Vicks, so used when people have colds. You switch that dash to a wedge, you have methamphetamine. Right. Again, it's just the difference between the three-dimensional structures. Now, people always are like, oh, so can we take Vicks? And no, they're different. Right? They're different molecules. But it's showing the difference between these two isomers. They are isomers of each other, but they are connected in space differently, and that gives them different properties, as drastic as this. Now, there is some, like in foods as well. Obviously, this isn't as drastic as thalidomide and as looking at Vicks versus meth. But plus and minus is similar to R and S. And you have lemons versus oranges. So when you're looking at different enantiomers, one is found in lemons, one is found in oranges. Obviously, that's a lot more similar than Vicks and meth. Another one, carvone. One is caraway, which is fennel. So fennel seeds have like a licorice taste versus spearmint leaves. Again, one is the R, one is the S. So, right, one of them is looking at the wedge, one is looking at the dash. So it's just these differences in enantiomers, right? They have different physical properties. They are different, right, different molecules.
How do you know which one's R and which one's S?
We're going to do that at the end of the week into next week.
Okay.
Have you ever seen Breaking Bad?
Yes.
Have you ever seen Walter White teach chemistry? You just said like the exact same thing that he said.
Uh-oh.
About the isomers.
Am I Walter White?
I think you can become Walter White.
Not old enough. Well, clearly. Anyway, so we're going to start by just looking at identifying chiral centers. So what I want you to do is I want you to look at these different carbons, and I want you to see, is it a chiral center? Right? If so, I want you to put a little asterisk next to that carbon. So for example, you want to look at where is a carbon potentially connected to 4 different things. And I notice here, this carbon looks like it could have 4 different things. If it helps you to draw the bond line structure, draw the bond line structure. This is just giving you the condensed. So this carbon is connected to ethyl, methyl, hydrogen, and chlorine. Are those 4 different substituents? Yes. This is a chiral center. All right, so go through and do that for the other 3. And I will give you a hint. Each one only has potentially 1 chiral center. All right, only has potentially 1 chiral center.
How you do this?
Well, first, you're just labeling chiral centers. Same thing.
Yeah, but like.
Has to be sp3 hybridized. Meaning it has to have 4 things attached to it.
Okay,
so
like this.
that could be one.
Okay, but like, how do you distinguish? Because you have C.
So then you're looking at like everything that it's attached to. Where is that?
Or like this one.
Oh, where is that? Oh. 4, 5 then. Yes.
Alright, I'll try it. No.
Okay, so for this practice, I tried to kind of look at each one of these. This one is not a chiral center. There are no chiral centers here. This is not a chiral center because this carbon is connected to 2 methyls, not distinct substituents. This one as well. This is an ethyl and an ethyl, and then a hydrogen and a bromine. 2 ethyls is not 4 distinct substituents. This one is because it's an ethyl, a propyl, a methyl, and a bromo. Okay, so then let's look at this one now. I'm going to give you a couple hints with this. So this is actually tetracycline. So if you've had an antibiotic recently after like being sick, this could be it. Tetracycline is a common antibiotic. With identifying chiral centers, some things I want you to keep in mind. It must be sp3 hybridized. Now you say, okay, what does that mean? Means it must be connected to 4 groups. Connected to 4 groups. The reason that that's important and the reason that I'm telling you that right now is because any of these carbons that have a double bond are not sp3 hybridized. They cannot be chiral centers. And then all 4 groups must be different. All 4 groups must be different. So I'm going to have you go through with your groups and see if you can find the chiral centers. And I'll give you a hint. There are 5 of them. Chiral centers. There are 5 of them. Remember this, right? This is a lone pair on it because if there was a hydrogen, you would see it if it's connected to a nitrogen. So work with your group. See if you can find the 5 chiral centers.
Teacher, what's like hybridization? Like sp3, what does it go to dax D?
sp3D and then sp3D2.
Is that the highest? How much time till we learn something new? If I go to the bathroom.
Yeah. Two, three, four, 5. Right? So any of these that have double bonds cannot be a chiral center. Has to be sp3 hybridized. It has to have 4 things attached. to even potentially be a chiral center. So this has 4 different, right? This, we're just kind of looking at everything else. This has this and all of this, and all of this. And we're just kind of looking. This is going to have this part of the molecule, this part of the molecule, and a hydrogen. Same thing over here, right? It's not symmetric. This one's a little bit easier to see 4 different things. This one as well. This is definitely a little bit more of a challenge with identifying chiral centers. Now, the other thing that we can kind of think about when we look at chiral centers is how many possible stereoisomers you could have, right? How many different stereoisomers, how many combinations could we make by switching wedges and dashes in all these different places? When we're looking at possible combinations, and we'll talk a little bit more about this tomorrow. So possible combinations, how many different stereoisomers can we have? It's 2 to the n. N is number of chiral centers. So for this, how many different stereoisomers could we have? It's 2 to the 5th, which is 4, 16 times 2, 32. 32 possible stereoisomers. And we're going to talk again more about that. This is just kind of a general intro today. Because stereoisomers are if we were to switch one of the wedges and one of the dashes, right, on each chiral center. What happens if we switch the wedge and the dash on a chiral center? And so that's looking at our chiral centers. Oh, I did this already. Okay, I animated it. Okay.
That sucks.
There we go. So, looking at asymmetric centers, and one question that I tend to get is, what's the difference between an asymmetric center and a chiral center? Nothing. Right? They're the same. An asymmetric center and a chiral center are the same. You'll also see the term stereocenter. So an asymmetric center and a chiral center are the same. When you hear the term stereocenter, that could actually be a chiral center, or notice how it's pointing to a carbon in a double bond. Cis-trans isomers are stereoisomers as well. Stereocenter is one place where if you switch 2 groups, you create an isomer. So that could be a chiral center, or it could be the carbon that's part of a double bond to switch from a cis to trans isomer. So again, this is just looking at some of those definitions to help us as we start to get into stereoisomers more. One kind of term that I want to talk about are racemic mixtures. So racemic mixtures, we're not going to deal a lot with racemic mixtures, but I just want to kind of introduce them. A racemic mixture is when we have a 1-to-1 mixture with both enantiomers. Now you're like, okay, so this is showing crystals, like what is that? Well, racemic mixtures are actually useful. Like if you're taking Advil, you have a headache, looking at your notes too long gives you a headache, you take Advil, it's actually a racemic mixture. They're using both enantiomers to help, right? That gives us the best combination to relieve pain. And so a racemic mixture is just a mixture with both the enantiomers, right? The R and the S. And again, we'll look at designating R and S later, but just knowing kind of racemic mixture is a mixture of the 2. We're not going to get into polarizing light a lot. Polarizing light becomes a lot more physics. Essentially, right, and you can see in all of your slides, this shows you normal light versus polarized light. So you put a polarizer on and it just goes in a single direction. Well, how is this useful for organic? A compound that is achiral, right? Achiral doesn't affect plain polarized light, right? Doesn't rotate it. It does not affect it. An achiral compound does not affect polarized light. A chiral compound does. So if you're trying to figure out, is this compound chiral or achiral, you can actually use polarized light. And what it actually does when you shine polarized light through the sample, it actually rotates the light. So achiral, we say, is optically active. We talk about the positive and the negative being the direction that it rotates. We don't focus on polarized light. There is math that goes along with polarized light. We don't do said math, right? We just, most important thing is that one property of a chiral compound is that it will rotate light. And so kind of some of these definitions, and this is in the intro activity and this is in your slides. A chiral molecule will rotate light. Its enantiomer will actually rotate the light in a different direction. So if you have a chiral molecule rotating light clockwise, its enantiomer will rotate it counterclockwise. Achiral will not rotate, and a racemic mixture actually doesn't rotate either because they cancel out. So you actually have it rotating one direction, but then the other enantiomer rotates it the other direction, and it will actually cancel that rotation out. Polarimeter, right, we're not going to do the math that goes along with it. If you're like, but I like math. Okay, well, we're not doing it. And so this is where that positive and negative comes in. Sometimes you're going to see that there's a positive in front of the name and that there's a negative in front of the name. That's actually based on the direction that it rotates light. It also goes along with the R and the S. So when we talk about R and S, we're going to use those letter designations. A lot of times you'll see like R or plus and then the name, or S or minus and then the name. And so the last few on here, and what we might do is we might actually just do these as the do nows tomorrow, is looking at, are these identical or are they enantiomers? And one thing before we kind of finish up for today, one thing that I do want you to keep in mind when you're asked if something is an enantiomer, remember it needs a chiral center. So needs chiral center. If it does not have a chiral center, it cannot be an enantiomer. So when you're looking at is it identical or is it an enantiomer, not only are we looking at can we rotate it and lay it on to the original, but we also want to see does it even have a chiral center first? Because if it doesn't, then they have to be identical. It means we flipped it in a certain direction. So we're going to stop there. We'll continue looking at these tomorrow. There is a video on Edpuzzle for chiral relationships, so just watch that for tomorrow so that we'll continue to go through practice with chirality, diastereomers, meso compounds, and we'll do some more practice with this tomorrow as well.